Good morning. So for today, we are going to be focusing on our notes for Concept 3. So we're going to, you guys will take some notes on here. Concept 3 notes start on your packet on page 25. So they look like this. So you'll have to skip ahead a little bit. Don't cross out anything yet. We might do that, some of those labs yet in there. There's one activity yet that I think I might do in there. So just because we're going over it right now doesn't mean we won't come back to it. So our Concept 3 notes is on states of matter, which we have briefly already kind of introduced here when we were talking about different properties and chemical changes versus physical changes. And we had touched on that physical changes include changes in states of matter. So this is like going from a solid to a liquid, from a liquid to a gas. All right, so we have an idea of what these are already, but we're going to take a closer look into this. So again, starting on page 25. So energy review. Some of this we have maybe, talked about. Some of this maybe isn't, review for you guys because we may not have gotten to this part yet, but we do have different kinds of energy. So we do have something called thermal energy. And so this goes under the energy review. Make sure you put this under energy review. So thermal energy is the sum of the kinetic and potential energy of particles in an object. All right, so thermal energy, usually we think of thermal energy as heat, right? And that's the basic definition of it. But on a molecular level, what we're doing is we're actually looking at how fast or how slow are those particles moving and how much more can they move. And so kinetic is the energy of movement, and potential energy is the, just like kind of the name implies, it's how much can it move yet. And so every object has a different type of, energy to it as far as how much it can and cannot move. So here this will go under thermal energy. So kind of indent this a little bit under your definition for thermal energy. And here we define the term kinetic energy. So kinetic energy is the energy that's in motion, and potential energy is stored energy. So both of those are good definition words to kind of remember moving forward. So I do recommend either highlighting those, underlining them, putting them in a different color, make them stand out, all three of those energy vocabulary. You do not have to write this. This is just as a reminder here. So this relates to matter, specifically how matter physically changes states through the motion of the particles within it. And so when we talk about different states of matter, we're not just going to be talking about solid, liquid, gases. We're going to be talking about what do their molecules look like? What are they doing in those particular different states, and how we change and move from one state to another, and how those particles or those molecules are changing. So again, you don't have to write this either, but a theory, explains what we know to be true about this. So we have our next part here that we're going to introduce called kinetic molecular theory. So kinetic molecular theory is number one. So you'll put this under kinetic. Number one's already written for you, so all you have to do is start writing it all. So all matter is made of small particles, either atoms or ions or molecules. Atoms would be single elements, like iron or gold or helium or hydrogen. Ions, as we'll get to know, are molecules that have charges to them. And then molecules, which would be like H2O, CO2, those, we know that they can be made up of either of those. So all matter is made up of small particles. And those particles, you a lot of times will draw as just circles, just like we see in the picture off to the side there. Those particles are in constant random motion. All right, and it's easy for us to maybe visualize that when we're talking about a gas and a liquid. It's a little bit harder for us to visualize that at a solid level, because we think that if it's solid, it doesn't move at all. But as we're going to see, it actually does. There is some small molecular vibration movement that happens within solids. But this motion is what will cause particles to collide with each other and the container that they're in. So they are bouncing around within that container, bouncing off the sides, bouncing into each other, and colliding with each other. And so the word kinetic means movement. So just remember that when you're talking about anything that has to do with kinetic energy or kinetic theory here is talking about movement. So we're theorizing that all of these particles are moving in constant random motion and they collide with each other and the container that they're in. We need to pause so you can finish writing these down. Go ahead. I'm going to move on. So what does this have to do with temperature? Well, again, temperature is, we just talked about thermal energy, and thermal energy has to do with temperature. It's basically a measure of an average kinetic energy of the particles in an object. Now, normally we would say temperature is a measure of how hot it is or how cold it is or something like that, which is a fine definition if you're just learning about the basics. But when we're coming back to this now and looking at this on a more of a scientific level, temperature is a measurement of the amount of movement basically within the particles of an object. And as you can imagine, we'll talk about what happens when you heat things up. How does that affect the movement? And when things are cooled down, how does that affect the movement? So this is what I was just saying right now. So this part here, you need to put this underneath temperature. So this should go indented a little bit underneath your definition for temperature. So the higher the temperature, the higher the kinetic energy, and the greater the motion of the particles. So when we increase temperature, we increase kinetic energy, which means the motion of the particles is also increased. So what that means is when you heat things up, those molecules, those atoms, those little circles that we usually draw, they're now moving a lot faster. They're moving around a lot. And it's easy to see why, right? We can, if you heat up a pot of water, you can start to see the molecules or the water itself moving and bubbling around. So when you increase temperature, you're increasing your kinetic energy and the motion of your particles. So you don't have to do this, but how does this connect to states of matter? So solids, liquids, and gases. So it seems to us like if you heat up, any of these, if you heat up a solid, you are going to get some more movement. If you heat up a liquid like water, you are going to get more movement that you can actually kind of see. A solid will begin to melt. A liquid will begin to turn into a gas. Now, gases are harder to see. But when you do heat up gases, they do start to move around even faster. And then let me hide that here. How do you think the motion of the particles differs in each state? So I kind of just mentioned that already. When we're heating things up, solids are more, they do start to, vibrate and move around a little bit more. Liquids move around quite a bit more, and then gases do too. So here are three main states of matter. We have solid, liquids, and gases, and we can see how the molecules look in each one of those, so make sure that you're aware of that. And I believe you should have these pictures as well in your book or in your on your pages here, and I think hopefully they're in color. But so this is the solid, this is the liquid, this is the gas. And you don't have to identify these because the pictures are just next to the words in your packet. So to finish off on page 25, we're going to start talking about a solid. So we have both a two-dimensional picture down here in the bottom of a solid and how the objects look and how they're just sort of like crammed into each other. They're taking up as least, the most amount of space as possible. Same thing with the three-dimensional picture up there. So solids are going to have what we call a fixed volume and a fixed shape. Sometimes we'll use the word definite volume and definite shape, but really they mean the same thing. So if you ever come across that word definite, it would mean the same thing. So what does this mean? It means that the particles are held tightly together in a rigid structure. So the volume is set. It doesn't change. Think of a pencil. All right. So whether you put a pencil on the counter or on the floor or, throw it up in the air, it's going to have the same volume and it's going to have the same shape. At this state, particles have very low kinetic energy. So this should all go underneath the fixed volume and fixed shape here part that you just wrote down. So particles have very low kinetic energy because they are, because they are held so tightly together. They'd have low kinetic energy, meaning that they're not moving very much. Because of this, the particle motion is limited to, as I said, vibration before. So solid particles, are they moving? Yes, but they are moving just very, very, very slowly. Actually, maybe very quickly is what we should say. They are more just of a vibrating kind of back and forth. So the molecules that make up your pencil or the table or your, bed, wherever it is that you're listening to this, they are moving, but they are moving at a very kind of like vibrational pace. So they don't actually end up, the solid structure doesn't itself end up moving. They just kind of vibrate back and forth. Okay, so again, we don't feel it, we don't see it. It takes place on such a small molecular level. So particles held tightly together, very low kinetic energy. Vibration is the particle motion. So I'm going to move on if you need to. Pause and take a second here for this. Go ahead. So liquids, look at their shape here in a three-dimensional structure and in just a two-dimensional structure down here in the bottom. We can see that a lot of them are touching each other like they were in the fixed or in the solid one, but their shape is different now. It doesn't really look like it has a definite shape or a fixed shape anymore, but they do still have what we call a fixed volume. All right, so a fixed volume, meaning that they take up whatever, the amount of space that they take up is still the same, but it is based on the shape of their container. The shape of the liquid changes depending on the container that it's in. So if you have a cup of water, let's say I pour 100 milliliters of water into a cup. Okay, so first of all, I put the 100 milliliters of water into a graduated cylinder. That was a fixed volume, 100 milliliters. And the shape of it, though, was the shape of the container. 100 milliliters is like a full graduated cylinder, right? So kind of tall and skinny. Now I take that water and I pour it into a cup, like a red Solo cup. Okay, how does that change shape? Well, it now is more wider and more spread out a little bit, but is it still 100 milliliters? Yes, it is. Okay. Now what happens if I take that water and I dump it onto the floor? Do I still have a fixed volume? Is that still 100 milliliters? Assuming I was able to transfer everything, yes. But the shape of water will change. Now it's going to take the shape of basically the as much room as it has to spread out on the floor. So those are all, still examples of liquids. So their volume is fixed. You have the same amount, but the shape can change depending on the container. Now let's talk about their kinetic energy and their particles and how they're moving. So the particles for liquids have more kinetic energy than solids. They're not super, super high kinetic energy, but they definitely have more kinetic energy than solids. You can see this. You can slosh around a container of liquid and see that it can move. You can't do that with a solid, right? So these definitely have more kinetic energy. And what the particles are doing, what those circles are doing, if you're looking at that, because that's what we're talking about when we're talking about particles. We're talking about those little circles that we're drawing. They can either flow or slide past each other and just sort of move around with each other. But a lot of times they're constantly touching, but they're very, very free-flowing. Whoops, let me go back to that. Okay. So more kinetic energy than solids, particles can flow or slide past each other. So I'm going to go on to gas. So gas particles have no fixed volume or shape. No fixed volume, no fixed shape. So what this means is that the gases, it is really hard to contain them in a volume because they are so spread out. So they are basically going to fill up whatever the container it's being held in. Whereas with the volume, with liquids, I could at least fix the volume, right? If I start out with 100 milliliters, that's what I'm going to have. With gas, it's very hard to contain that unless you're using some type of condenser type object. But if confined, the gas particles will spread out to fill the container. Now, the container could be like our room, all right, or your room, or wherever that you have air and gas all around you. It is taking up every single corner of your room. Okay, getting into underneath your bed, or if you're, here at school, it's getting underneath the table and in every cupboard, and it's filling out everywhere. It's spreading out everywhere. Okay, there's virtually no place where you're not going to have gas in wherever you are. All right, unless you're talking about some like vacuum type of system. Alrighty, so the gas particles will spread out to fill the container. So they have no fixed volume or shape. They call the shape of themselves can be spread out too. The only way that you could do that is like here you have a picture of like a flask with a stopper in it, right? And if I would just look there and say, what's in here? You'd say nothing. And I would say, yes, there's gas particles in there. The spreading out to fill the container is also known as diffusion or gas diffusion. All right, and next year in biology, guys, we'll learn a lot about diffusion from Ms. Reinertz as well, talking about like how particles move across membranes and things like that. With gas particles, these particles are moving around a lot, and so they have a high kinetic energy, a high energy of movement, and they are constantly bouncing into each other and off of each other. I know you're looking at a picture here that just looks like they're stagnant, but this is just a snapshot of time. These particles are actually moving at a very, very, very high rate and just smashing into each other and the sides of the container, if you can contain them at all. So the energy is high enough because they're moving around so much that they're able to overcome any forces that kind of would hold those particles together. So that's why gases are able to just kind of be loners themselves and able to mix, in with other gases because there's virtually no force that will bring them together as long as they're able to because they have that high kinetic energy. So they're moving around so fast that you'd have to have some sort of, force powerful enough to bring those particles together. And there are a few forces that can do that, but not anything that we're going to get into right now. Okay, so I think that is enough for today. So make sure that you have all of these notes done, and I will have a Shobi Dropbox for you to submit these to. So look for that. It'll be titled probably Concept 3 notes, page 25 and 26, even though we just did half at 26. So please submit these to Shobi. Thank you. Oh, I'm sorry. Whoops. I have one more thing down there. I forgot. Particles can freely move. All right. So hopefully got that last little bit there. Particles can freely move. So submit that and you're good to go.